Phase contrast microscope. Principle. Phase contrast microscopy is a technique used to enhance the contrast of transparent and colorless specimens without the need for staining. The principle is based on the fact that different parts of a specimen have different refractive indices, causing light to slow down and change phase as it passes through them. By converting these phase shift into changes in amplitude, phase contrast microscopy makes these structures visible. Structure of a phase contrast microscope. A phase contrast microscope is composed of several key components, each contributing to the generation of the phase contrast effect. The light source provides the necessary illumination, which is then shaped into a hollow cone by the annular diaphragm located within the condenser. The condenser focuses this cone of light onto the specimen positioned on the specimen stage. Objective lenses collect and magnify the light that passes through the specimen. These objectives are equipped with the phase rings essential for phase contrast. A phase plate situated in the objective lens or condenser shifts the phase of the background light relative to the diffracted light, thus creating the phase contrast effect. The image is further magnified by the eyepiece for the observer. Proper alignment of the phase rings in the condenser and objective lenses is achieved using a phase telescope. The microscope also includes focus knobs for coarse and fine adjustments to achieve sharp focus and mechanical stage controls for precise movement of the slide. Additionally, an illumination intensity control allows for adjusting the brightness of the light source. Each of these components plays an essential role in ensuring the microscope effectively visualizes transparent and colorless specimens with the enhanced contrast. Working mechanism. The working mechanism of a phase contrast microscope involves several key steps. Light from an illumination source passes through an annular diaphragm, which shapes it into a hollow cone. This cone of light then illuminates the specimen, where different parts of the specimen cause variations in the speed and phase of the light due to their different refractive indices. As the light continues through the specimen, it encounters a face plate situated at the back focal plane of the objective lens. This plate is specially designed to either retard or advance the phase of the background light relative to the light that has been diffracted by the specimen. When these phase shifted light waves recombine, they interfere with each other, transforming the invisible phase differences into visible differences in amplitude or brightness. This interference enhances the contrast, making the transparent or colorless structures of the specimen visible without staining. Thus, phase contrast microscopy allows for the detailed observation of living cells and tissues in their natural state. Resolving power of the phase contrast microscope. The resolving power of a phase contrast microscope is crucial for distinguishing between closely spaced points in a specimen and is influenced by several factors. Central to this resolving power is the numerical aperture of the objective lens. A higher numerical aperture results in better resolution. Additionally, the wavelength of the light used for illumination plays a role. Shorter wavelengths offer improved resolution. The theoretical limit of resolution can be calculated using the formula d is equal to 0.61 lambda divided by Na, where lambda is the wavelength of light and Na is the numerical aperture of objective lens. For visible light with a wavelength around 550 nanometer and a high numerical aperture lenses, the resolving power typically ranges from 200 nanometer to 300 nanometer. However, practical resolution may be slightly lower due to optical aberrations, and the quality of the phase contrast components, while phase contrast microscopy enhances contrast and allows for the visualization of transparent specimens without staining. It does not significantly improve resolution compared to bright field microscopy. Its primary advantage lies in its ability to make transparent and colorless specimens visible rather than in achieving superior resolution. Advantages of the phase contrast microscope. Phase contrast microscopy offers several significant advantages that make it a valuable tool in various scientific fields. One of the primary benefits is that it does not require staining the specimen, allowing for the observation of live cells and tissues in their natural, unaltered state. This preservation of viability and physiological functions is crucial for studying dynamic processes. Additionally, phase contrast microscopy significantly enhances the contrast of transparent and colorless specimens. By converting phase differences into intensity differences, it makes otherwise difficult to see structures such as organelles within cells clearly visible. Since no staining or other potentially harmful preparations are needed, the technique is not destructive to the specimen, allowing for repeated observations of the same sample over time. This capability is essential for studying dynamic processes in living cells. The technique also allows for detailed observations of internal structure within the cells and tissues, which is crucial for cell biology, microbiology, and medicinal diagnostics. Moreover, phase contrast microscopy is particularly useful for live cell imaging, enabling researchers to study cell movement, growth, and division in real time, providing valuable insights into cellular processes and interactions. Once properly set up and aligned, phase contrast microscopes are relatively easy to use, making them accessible for routine laboratory work, educational purposes, and advanced research applications. These advantages make phase contrast microscopy an indispensable technique in biological research, clinical diagnostics, and other fields where visualizing transparent specimens with high contrast is necessary. Disadvantages. Despite its many advantages, phase contrast microscopy has several disadvantages that limit its use in certain applications. One, one of the primary drawbacks is the halo effect, which can produce bright halos around the structures in the specimen. This effect can obscure fine details and make it challenging to interpret the image accurately. Additionally, phase contrast microscopy requires a complex setup and precise alignment of components such as the annular diaphragm and faceplate. This complexity can make it more difficult to use and maintain compared to simpler microscopy techniques. Another limitation is that phase contrast microscopy is best suited for thin specimens. Thick specimen can cause multiple phase shifts and scattering of light, resulting in poor image quality and reduced contrast. Furthermore, the technique is less effective for specimens with little variations in refractive index as it relies on these differences to create contrast. In some cases, phase contrast microscopy may also introduce artifacts due to the interactions of light with the face plate, potentially leading to misinterpretation of the specimen's features. Lastly, while phase contrast microscopy enhances contrast without staining, it does not provide color information. This can be a limitation when color differentiation is necessary for identifying specific structures or components within the specimen. Despite these advantages, phase contrast microscopy remains a powerful tool for observing live cells and transparent specimens, but it is essential to aware of its limitations and potential artifacts when interpreting the results. Applications of the phase contrast microscopy. Phase contrast microscopy is a versatile tool with numerous applications across various scientific and medicinal fields. In cell biology, it is extensively used to observe live cells, enable researchers to study processes such as mitosis, cell movement, and intercellular dynamics without staining. This capability is crucial for examining cell morphology and interactions in their natural state. In microbiology, phase contrast microscopy allows for the detailed observation of microorganisms like bacteria, protozoa, and algae, providing insights into their behavior, growth patterns, and cellular structures. In histology, it facilitates the examination of tissue sections without staining, aiding in the study of tissue architecture and the identification of various cell types and structures. The technique is also valuable in clinical diagnostics where it is used to analyze clinical samples, just blood and urine, assisting in the identification of cells and microorganisms for disease and infections diagnosis. Additionally, in developmental biology, phase contrast microscopy helps researchers observe developmental stages of embryos and other organisms, offering insights into morphogenetic changes. In pharmacology, it is used to assess the effects of drugs on living cells, allowing for real time observations of cellular responses and drug mechanisms. Lastly, in aquatic biology, phase contrast microscopy is employed to study microorganisms and algae in natural water environments, contributing to the understanding of their ecology and behavior. Overall, phase contrast microscopy provides high contrast visualization of transparent and colorless specimens, making it an invaluable tool in both research and clinical settings. Thank you.